Okay. Okay. So can you hear me at home? Awesome. Thank you. Sorry for the complication there. Okay, so let's go ahead and start. And folks can hear me at home, okay? Yes, great, thank you. So there are two things, well, sort of three things to talk about today. The first is the state of the assignment that's due Friday, and what questions people have about that. I've had one actually before class even started, which I will repeat because I think it might be relevant to multiple people. But I'd love to take any other questions about that assignment. And then based in part on the sense of how people are doing on the assignment and what questions people have, we need to talk about Friday and what's going to happen there. And that will become clearer when we get to it. And then the third thing is, if time allows, we'll talk about changing the frequency of a sound in jazz. But the main thing I want to focus on first is the assignment. So there was a question before class started that most of you wouldn't have heard, which was on the first problem on the assignment, you're supposed to change the volume of a sound. And the assignment says to play both the original sound and the modified sound so that we can hear how the volume has changed. So the goal is to try to simplify the grading experience, really, so that we don't have to like remember to play the original sound, then modify it, then play the new sound and make sure that we're hearing the difference between the two. Zeke was having a problem where if he was playing the two sounds, one right after the other, only one of them was actually playing. So if we define I guess I should share screen, just if we define play two sounds, and we do play A and play B. And today is, oops, I'm in the wrong place. Yeah. CSci 1201, 2020, 10. Today is the 14th.py. And so if I say airplane is make sound, pick a file, and I go get airplane, and I say about is make sound, pick a file, and I choose about. Now if I say play two sounds, airplane and about, oh, right, I've got to change momentary pause while I make the volume on my phone go to 0 and have volume on my laptop. Oh, that's not good. Maybe I have to take my phone out of this. Okay, I'm gonna log off on the phone because I think that's gonna give us trouble. Okay, can you still hear me at home? Cool. And I think I can hear what's going on here. So I'm going to play this. Oh, a local or global name. Did I not load? Oh yeah, I didn't load. That matters. Airplane. So you can, the two of them sort of overlap. And because airplane's longer, I think you get a little bit of it sticking off on the end. Airplane. Which is not sort of the desired effect. Can you hear that at home, by the way? Okay. And can you guys hear? Okay. So the problem is if you just say play, it starts playing in the background and immediately moves on to the next command. And in this case, that's another play. And so it starts the second play on top of the first play. And the two of them interfere with each other badly. So there is an alternative, which is blocking play. I think that way, yeah. And blocking play says, I'm going to wait until that sound has completely played before I move on to the next command. So here it will play A in its entirety and then move on and play B. Okay? And so now airplane about. It gives us the sequence of sounds because it waits for A to finish before it moves on to B. And so that's what you would need for that first exercise to make sure that you hear all of the first quieter version before you play the second louder version. So does that make sense? Questions about that anywhere? Other questions about the assignment? Anybody at home have a question? Okay, nothing? Now it's unclear to me how to interpret this. This could be, oh, it's Wednesday and the assignment's not due for 2 days. Why would I have started it yet? And that's legit. I mean, we all make choices, and certainly I do a lot of less things at the last minute myself. Or it could be, oh yeah, did it, no problem, everything's good. And I'm not sure which of those two things it is. But it would be useful to know. So here's the issue that makes this sort of more important than it might otherwise be. And the issue is I won't be here Friday. So I will be here in Morris because I never go anywhere anymore. But there is a programming competition, and I'm the coach or advisor for the programming team. And normally this competition is up north, but it's all being held online. But from 8 a.m. till 5 p.m., I'm sort of supposed to be at this competition. And so I won't be in class on Friday. And so normally, you know, we could say, oh, the assignment's due Friday night. Everybody looks at it for the first time Thursday night, comes in Friday in a panic with a bunch of questions and gets them answered. But hey, I'm not going to be here Friday to answer your questions, so that's not going to work as well as it might have otherwise worked. And so it's not entirely obvious what to best do about that. I think what I'm gonna do for the moment, and you can all yell at me as you work on this and tell me this is a terrible, terrible idea, but even though I'm not gonna be here, this Zoom room will still exist Friday, and you can still join it, right? And you can actually talk to each other. You are adults who know things and are smart and helpful. You could use that time as a shared time to work on the assignment. And you can support each other and answer questions. And then during class, feel free to like ask questions on Slack. Depending on what they're expecting of me, it's unclear because we've never done this thing online before. I don't know how busy I'll be Friday. I may, in fact, have almost nothing to do. In which case, I would be happy to like be answering questions on Slack even during class if I'm not doing something then. On the other hand, they may have a whole set of activities that I'm expected to participate in which case I will be less able to assist in a timely manner. But I will give it a shot. So let's say the Zoom room will be open, so you should be able to join the class online, just like you would normally. I won't be there, but you're all, you know, able to join and talk to and help each other. And I would seriously encourage you, if you get stuck, if you have a question, ask the room and see if somebody's got a solution. Like I know there are people that knew this blocking play thing. I also know there are people that didn't, right? So it was good to go over it. But if that had been asked Friday, I think there are people here who could have answered that and helped each other out. So I'm going to say, you're adults. You're going to do awesome work on Friday. Ask questions on Slack as they come up, and I will attempt to answer them there. And that will be the plan. And if that blows up, we will adjust accordingly. But fingers crossed, that'll work out okay. So, questions about that? And or questions about the the sound assignment, not the first assignment, the chapter 7 and 8 assignment. Any questions here in the room? Any questions online? Okay, well then, we're going to talk about changing frequencies. And I think it was Nick asked a question as part of last Friday's little discussion assignment about modifying frequencies. Am I right? Was that you, Nick?
Yep.
Okay, cool. And so I answered some of that on the discussion, but I don't know to what degree people saw that. And I want us to talk about frequencies a little more because it will be part of not the assignment that's due Friday, but the next assignment after that actually requires that you do some frequency manipulation. So I want to talk about what the issues are there and how we might address them. Okay, so I'm going to share. Are there questions about anything before I share the whiteboard and we draw some pictures? Okay. So, so let's imagine, oh, come here. There we go. Let's imagine we have a sound wave. And it's like, okay. We got a sound wave. And we're sampling it at a certain rate. So we're collecting samples at some rate. And then the computer reconstructs the sound wave by trying to build the curve that goes through those samples. And if we want to change the frequency, let's say we want to make the frequency higher. If we want to change the amplitude, we just need to like shift things up and down. That will make things louder or quieter. That part turns out to be pretty easy. The frequency is actually much trickier. So here, if we wanted to make this frequency higher, we need to make the uppy downy bits go faster. So instead of taking to get to here to go up and down, we're going to have to maybe do that in this amount of time. Oops, I didn't do that very well, but whatever. And then we need to come down and up, but again faster, and then there's over a little bit and under and over. And one mistake I'm making is I'm also sort of shrinking my amplitude, and that wouldn't normally be part of this. So that didn't do a very good job of compressing it because I don't art well. But that's the idea, is you're taking that the curve on the top and you're squishing it in so that the whole thing happens, in this case, like roughly twice as fast. And that will change the frequency. In this case, it would make the frequency higher because the movement up and down is more rapid. The frequency here is going to go up. So this would become a higher pitched sound. And so if this was like human speech, this would make that human speech more chipmunky, right? It would get that high squeaky sort of thing. Notice it will also make it go faster. So it will change the pitch, but it also changes the speed. So if it took the person 5 seconds to say something before, now they're going to say the same thing in 2.5 seconds. So that the speed changes as well as the pitch if we do this. And we could also, elongate things by, like if this was supposed to end here, we could make it end out here. Right, we could stretch things out. Blah, 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 blah. And that would make it a lower pitch, but it would also be slower. Okay, it would take longer for the person to say the thing. This is the same effect you would get if you manipulated the speed of a tape. So if you had a cassette tape, I know that's an ancient technology, but you might have seen them on TV. Or even more ancient for most people, a reel-to-reel tape deck, and you change the speed, if you sped it up, things would get a higher pitch, but they would go faster. And if you slowed it down, things would get a lower pitch, but they would go more slowly. Or if you had a turntable with an LP, if you change the speed that the LP plays at, the pitch will go up or down and the speed will go up or down. So if it's a 33 1/3 RPM record and you play it at 45, it will be a higher pitch and the record will end faster because everything goes faster. And if you have a 45 and you play it at 33, that would slow things down. So this is a simple way of dealing with this. And that's what we'll basically work on today. An important and interesting question is, can you do this without changing the speed? Is the pitch and the speed, are they like inherently tied together in a way that you can't separate? And the answer is sort of, but not entirely. But the answer for this class is yes. You cannot pull them apart. That requires math that is way out of our pay grade to fix. So for us, changing the speed will change the speed will change the frequency, changing the frequency will change the speed, and the two are tied together, and there's not anything we're going to be able to do about it here. If you have higher end tools, you can in fact separate those things out to some degree. And certainly like sort of pro grade sound editing tools give you pitch shifting ability that doesn't modify speed. But even good free tools, so there's a program that I like a lot called Audacity. It's a free open source sound editing system, and it has pitch shifting available as one of its effects that you can apply to a sound. And essentially what these are doing is they are using the frequency spectrum and manipulating what's happening in the frequency spectrum and then coming back to sort of the sound wave spectrum. And like I said, the math there gets pretty sophisticated. There's a whole Wikipedia page on, I don't know if it's called pitch shifting or pitch change, something like that. And you can quickly find yourself in the middle of a bunch of fast Fourier transforms and other math that we are not going to enter into here. So we're just going to do the version where we change the frequency and the length together. And that's all we're going to be able to do in this class. If you want fancy, you'd need to probably, explore something like Audacity, or if you happen to, for some reason, have access to like some of the Adobe stuff that does higher end sound manipulation, it would work, blah, blah, blah. Okay, questions about all that setup? Anybody? Going. Gone. Okay, so how do we do this? Well, the doing it is actually pretty straightforward. If you think about it, to go from here to here, change my color. To go from here to here, we could just throw away every other sample, right? If we just threw out every other sample, then we get half as many samples here. So we would cut the time in half and we would double the frequency. So the uppy downy bits would happen twice as fast as they did before. Okay? And that's actually a pretty straightforward thing to do. And that's the first thing we'll try to do today. Now this has implications for what kinds of sounds we can reasonably capture. Like we're losing information when we do this. If you think about it, if we get rid of every other sample, we're inherently getting rid of information. There's information in the original sound wave that we're going to lose and that we cannot get back. And in particular, that information tends to be about the high frequency components of the sound. If you remember the Nyquist theorem that they talk about in chapter 7, to capture a frequency of n hertz, you need to sample at least 2 times n times per second. And so if we start out with, let's say 22,000 samples a second, which is what most of the sound files that the book provides are sampled at, that means our sort of highest frequency is about 11 kilohertz. So 11,000 hertz is about the highest frequency that we can capture at that sampling rate. And if you remember, the human hearing goes up to about 20,000 hertz. And so we're already unable to capture a whole bunch of high frequency sounds that the human ear is typically capable of hearing. And if we drop the number of samples, we sort of throw away a bunch of samples, then in some sense, this is effectively like bringing the sampling rate down to 11,000 samples per second. Oh, I should say per second. So we're actually looking at like 5,500 hertz. Now, it isn't really 11,000 samples a second because it's still 22,000 samples a second. We're just squidging them all in. So it's like we lose some high frequency information, but then we make everything a higher frequency. So you are ultimately losing some high frequency information, but it's masked by the fact that we chipmunk everything to death. But we're definitely losing information. That's, you know, the key thing. And then the other, if we go the other direction, we could just, if we come down to here, we could do that by doubling every sample. Would be a simple way to deal with that. If we repeat every sample twice, that will double the length of the sound, and it will effectively double the frequency, make everything a lower frequency. It creates some potential effects because we get sort of a stair-steppy kind of thing because we're repeating samples. And there are some ways we could fix that. We could take averages of samples to try to smooth that out, but we'll just double them, and that'll be the deal. Okay. So questions about that before we actually go to Jess and try to do it? Questions here in the room? Questions online? Anybody? Going, on. Okay. Then let's switch back over to Jess and let's see if we can make this thing happen. Share Jess. Away some. Okay. So, in fact, I'm going to load up anti-disestablishmentarianism. I'm just going to call that anti. It's nice and long, so we can hear stuff. I think that's something. Nope, that's Anthony. There it is. Anti-disestablishmentarianism. Okay. So play anti-disestablishmentarianism. There we go. Nice long word. Def. Right. Double frequency. Sound. And so what we were going to do here is we were just going to get rid of every other sample. So I'm going to have to make a new sound. I can't do this in place because the resulting sound is going to be half as long as the original sound, right? So I'm changing the size of the sound. So I'm going to need, excuse me, a new sound. So at first I need to figure out how big the current sound is. So length is get length. We'll call that source length. Get length sound. Okay. And now the target length is going to be twice the source length. Oh, half the source length. Sorry, we're going that direction. Okay. And then I need to basically grab every other sample and put it in. Oh, I need to make the target sound. make empty sound, and I'm going to say the length is target length. And now I want to go through and get every other sample from the source and put them in the target. Okay? And I could do this either of two ways. I could loop over the target samples and then go and grab the correct sample from the source, or I could loop over the source samples and put the right ones into the target. It doesn't really matter which one I do. I'm going to actually loop over the target samples because I know there are fewer of them. And so that will make this go a little faster. So for index in range target length, then the value is get value at, nope, get sound value at, sample value at. Can't spell. So I'm getting the value from the source sound, and at what position? Well, if index is where I am in the target sound, I want to get the sound from position 2 times that in the source. So if I'm doing sound position 4 in the target, I want to get the sound that was at position 8 in the source. And then 5 should come from 10, and 6 should come from 12. So I want to be going farther and farther out. And that's how I'm going to ignore every other one. Basically, I'm going to only take the even ones in the source, 0, 2, 4, 6, 8, and put them in the position 0, 1, 2, 3, 4 in the target. Does that make sense? Would a picture help there, or are people okay with what I'm doing on that? We good? Okay. Can I get a thumbs up or two from the folks at home, if that made sense? Okay. Coolio, thank you. Okay, then, so I'm going to grab the sound at position 2 times index, and then I'm going to put that in the canvas at position index. And then I'll return the canvas when I'm done. Okay, so questions about that before we try it out? Double frequency NT. Oh, did a bad thing. Inappropriate argument type. Set sample at takes 3 arguments. Oh, I forgot to give it the value. Duh. So it takes the sound, which index we're modifying, and the value we set there. I forgot to give it the value. Oh, that's better. Now we'll see what that looks like or sounds like. Did you hear that at home? Cool. So obviously that's very fast and very squeaky, right? That's like really not understandable. I think very few people, if you just played that for them, would at least easily be able to figure out what was being said there, right? We've really chopped this up pretty hard. And you can hear that the frequency has gone up. We play anti-disestablishmentarianism, and then, right, there's much higher frequency, and it finishes a lot faster, okay? So we're able to increase the frequency and have the speed, the total length, to double the speed. And it worked. It's not necessarily super understandable, but it worked. Okay. Now, if we wanted to make it more understandable, we could try to, instead of getting rid of every other sample, we could get rid of every third or every fourth, right? And that would also speed it up, but it would be less dramatic, and we would still expect some rise in frequency and some shortening in length, but it might be more understandable. So why don't we try to do that? Questions about anything here before we actually look at trying to be a little more flexible about how many, when we throw them away? Questions? So, if I want to drop every nth sample, let's do this. We'll say we're going to take a second argument n, which is how frequently do we want to drop a sample? If we put a 2 there, we're dropping every second sample. And that would be the same as what we just did. We throw away half the samples. If we put a 10 there, we're going to say, let's drop every 10th sample. So we'll do the first 9, skip the 10th, the next 9, skip the 10th, the next 9, skip the 10th. Okay? Does that make sense as a plan? Okay, now here, we're going to be able to do something similar. So we're going to need to get the source length. I think I called it source length. And now the target length is not going to be half. It's going to be sort of it's going to be the source length minus 1 over n times the source length. If we're going to throw away every 5th sample, then we're throwing away 1/5 of the total number of samples. Okay. And now that we can simplify that with a little math. Let me actually just change this to divided by n. No, actually, I'm not going to do that because I want to, yeah, I do want to do that. We'll just divide by n. We'll do that. So it's the source length minus source length divided by n. So if this is 2, we're subtracting a half of the source length and we'll get back a half of the source length. If this is 3, we'll subtract a third and we'll get 2/3 left. If this is 10, we'll subtract a 10th and we'll get 9/10 of the source length back. So that should give us the target length. And then we need to make an empty sound of length, target length. Okay. Now we got to loop over something and figure out what to do. And here I'm actually going to loop over the source length because I think it makes the math a little easier for me to think about. So for index in range source length, we need to just, oh, and I'm going to need a target index, which is 0. So that's going to keep track of where we are in the target, because we're going to sometimes copy into the target and sometimes we'll skip one. And so I need a separate counter to keep track of where we are in the target. And there are a number of examples in the book where they do this. And that's going to be a useful technique here, because I'm going to have to decide for each sample, hey, does this sample get copied or not? And the way I'm going to do that is I'm going to say, is the index a multiple of n? If we're going to drop every fifth sample, I'm going to drop the sample at position 0, 5, 10, 15, 20. We're going to drop every third sample. I'll drop at 0, 3, 6, 9, 12, dot, dot, dot. We're going to drop every seventh sample. I'll drop at 0, 7, 14, 21, dot, dot, dot. So if it's a multiple of n, then I'll drop it. Otherwise, I'll copy it over. That's the plan. Does that make sense? Now, the question is, how do we decide if something's a multiple of something? Okay. And let me, that's not going to be in there. I'm just going to have to do your guess or search. Oh, that is right. Okay. So the percent sign in Python, and this is true, this is a Python thing, and this is true in many, many programming languages. The percent sign gives you the remainder of dividing the first thing by the second thing. So if you think back to the old quotient remainder way of thinking about division, percent sign gives you the remainder. So slash gives you, for integers, oh, that was a poor choice. Let me do 28 divided by, gives you the quotient, and percent gives you the remainder. So 28 divided by 5 is 5, remainder 3. Because 5 times 5 is 25, 3 left over. So we can use that to decide if something's a multiple of something else. Because if I say 28 divided by 5, remainder 5, I get 3. The fact that that's not 0 tells me 28 was not a multiple of 5. But 28 mod 7, remainder 7, is 0. That tells me that 7 goes into 28 an exact number of times with no remainder. And so that tells me that 28 is, in fact, a multiple of 7. And so we frequently use this, and this is called the mod operator, which is short for modulus or modulo. So I'll frequently say things like 28 mod 7. If the percent thing gives us 0, we know we have a multiple. So I can say here, if index mod n equals 0, then I don't, oh, actually, I don't want to do anything. So really what I want is if it's not equal to 0, I want to do something. So if it's not equal to 0, I want to copy, get the value out of source, copy it into target, and increment the target index. So value is get value, sample value at. That takes a sound, which is sound, and a position, which is index. And then I want to set sample value at, which takes a sound, which is canvas, an index, which is target index, and a value, which is value. And then I want to increment target index. So I want to move my marker forward by 1. There's no else statement here because if it is equal to, if it is a multiple, we're just skipping it. So there's nothing to do there. And then we return canvas when we're done. And so we could say, well, let's first confirm that if we give it 2, what did I call it? I called it drop every, well, actually, let me make sure I got the whole thing here. Oh, stop it. Let's make sure we got the whole thing visible, Does anybody have any questions about this before I just start doing stuff? There's a lot going on there. This is a little more complicated than a number of the other examples that we've seen. So you should totally feel free to ask questions. And if this remainder thing makes your head hurt, definitely ask about that. Any questions at home? Good? Okay. Well, then let's press on. So loaded the program. So let's first see if dropping every second sample sounds the same as our previous thing. We had fast anti, so this is what we had before. They sounded pretty much the same. So that's a good sort of sanity check that this more complicated thing is doing the right thing. So let's try some other numbers. We'll just try a bunch of numbers until we find something that's maybe a little more understandable. So we'll try it with 3. Now that's pretty understandable. The pitch is clearly up, like it is a higher frequency, and it's a third as fast, but it's more understandable. You can sort of tell that that's the word. And if we say drop every 4th, oops, I must have typed something wrong. Oh, I said drop every 4th instead of drop every nth. That's entirely understandable. It's a little higher. We play original.
Anti-disestablishmentarianism. Anti-disestablishmentarianism.
Right? It's definitely higher pitch, and it's faster, but it's entirely understandable. And I suspect we won't do a million more of these, but if we tried running out to dropping every 10th sample,
Anti-disestablishmentarianism.
that's almost the same, right? Here's the original.
Anti-disestablishmentarianism. Anti-disestablishmentarianism.
So it does pitch up slightly, but it doesn't sound unnatural, right? Whereas like anti-3 even, oops, that clearly isn't, like you can tell that's been manipulated. And 4 doesn't sound supernatural either. But 10
Anti-disestablishmentarianism.
doesn't necessarily sound manipulated. Like if you didn't know what the original sounded like, you might be like, yeah, I'll buy that. That could be like a real recording. So that 10% raised it some, but didn't make it crazy. Okay. Questions? So we try to make something longer and have a lower pitch. Cool. Then let's try double frequency. And so here we'll just double every sample. So source length equals the same thing, target length. Cannot type today. It's going to be twice the source length. Canvas, make empty sound, target length. I'm repeating this enough that it makes me really want to make a function that just does that part, but I'll skip that for today. And then let's go ahead and actually do the target index equals 0 thing for index in range source length. And here, we'll always copy over, so we don't need an if, but we'll copy every sample twice into two adjacent locations. So we need to get the sample value out of the source. And we want to set the sample value at canvas target index value. And we want to increment the target index. And now we just want to do this again. You're going to want to repeat these two lines a second time. Oops, lost my indentation. So we're going to set it at this index, add 1, so we move the index forward, and then we set the value at that new index as well, and then move the index forward again, so we're ready for the next sound value the next time through the loop. So this essentially makes 2 copies of every value in the target sound. And then we return canvas, and we should be done. Questions? Now here I will double the frequency of airplane so we don't get like a super long sound. Whoa. Oh, I said double frequency and I meant to say half frequency. Oh man. So I actually just redefined another function with the same name as the earlier one. And one thing this illustrates is that in Python, you can define the same function twice and the later definition will win. If you define something 2 times, the later definition is actually the one that's going to take. Oh, I'm sorry, the earlier one is the one that took. Because we used this one, not this one. So this, hopefully, will, you want to say half frequency. Much lower frequency, sort of understandable, but not super understandable. Like it's really muddy. Ooh. So I think because we knew he was saying airplane, like we could probably tell that he's saying airplane, but if you played that for somebody and they had no idea, I don't know that they'd be able to figure out what that was at all. So lowered the frequency, but slowed it up so much that it's not really super understandable anymore. Okay. And we could do something similar where we don't double every frequency, but we double every nth frequency. And that would give us the flexibility of having less stretch and give us some additional understandability. We wouldn't necessarily come down this low, but we'd be able to get sounds that were a little more understandable. We've got 15 minutes, so we could totally just do that. That wouldn't be that hard. But are there questions about it? I feel like I'm just talking at a mile a minute here. And I would love to have some questions rather than me just like banging code out.
I have a question.
Yes, please.
So you set 2 index, the target index and the index, right?
Which one are we in?
I mean
Which
there are 2 index, the target index
Oh,
and
yes,
the
right.
index, right?
Right.
So can we just delete the target index and replace every index replace every target index to index?
No, not, well, you could sort of, but you'd have to have a lot of math. So to illustrate that, let me run back to the whiteboard and I'll try to illustrate why it's useful, if not even necessary. Oh, did I just undo that? I did. Ah, what did I do? Whiteboard again. Okay. So let's make a new screen. Let's imagine we're copying so we're copying from there. So this is the source. And this is going to be index. Okay. And we're going to have our target. Okay, target index. Now, we're copying from here to here. Let's say we take, let's consider the last one where we're cutting the frequency in half. I want to copy, let's see, if the values up here, let's get another color. Let's say the values are A, B, C, D, E, F, G, H, and I. If I'm going to cut the frequency in half, I want to copy every value twice. So I want A to be here and here. And I want B to be here and here. Okay. Now let's consider that we have done those two steps. Then at that point, index is pointing at C. C is the next value that index that we want to copy over, but target index needs to be pointing at slot 4 because the first copy of C needs to go here and the second needs to go here. So index and target index aren't pointing at the same thing, right? They're moving at different speeds. And if we jump ahead another couple of steps, and let's say we get C here and D here, now index is pointing at E, slot 4, because that'll be the next value to copy over, but target index is going to be pointing out at 8 because that's where the next copy, the next value is going to go in target. So index and target index move at different speeds. So it's useful to have them both in the program as separate variables so that we can increment one at one speed and increment the other at the other speed because they're not going to line up. If we're just copying one sound into another without any manipulation of the frequency, then yeah, we can usually just have one index and maybe an offset to sort of say where it's going to go. But if we're manipulating the speeds, it's often easier to have two indexes, one that tells you where you are in the source and one that tells you where you are in the target. Okay. And that was particularly true, I think. Well, actually, questions about this example before I make another example? Did that help you, Bo?
Oh, yes.
Okay. So the more complicated one in some ways is, let's do this color. The case where we were doing dropping every nth. Here, if we're going to drop every fourth, say, we're going to drop A, then we'll have B, C, D. We'll drop E, then we'll have F, G, H. Then we'll drop I and have J, K, L. And so in the first example, the green and the blue, you could actually get away with just doing some like multiplication. Like E goes into position 4 times 2 is position 8. So you could use index times 2 to get this spot, and index times 2 plus 1 to get this spot. So you could do some math to avoid having target index and just do all the math off of index itself. But here that becomes much more complicated because now you have 1 goes to position 0, and 2 goes to position 1, and 3 goes to position 2. 4 doesn't go anywhere. 5 goes to position 3. 6 goes to position 4. Like the math gets real weird there. There are some ways you could do it. It would be like index divided by, or index minus the number of times we had an exact multiple previously. But it's just easier at this point to have target index be a separate thing that gets incremented whenever we actually do a copy than to try to figure out the math in that case. And that's sometimes the case that there might be math that would work, but there's a simple non-math way to deal with it that works fine and is easier to think about. And I think for this, drop every third thing, or in this case, drop every fourth, it's easier to not try to do the math and instead just manipulate the counters accordingly. So that's a really good question, Yubo. Did that help? Does anybody have a follow-up question on that? Cool. Glad to have helped. And the book has a number of examples, even back in the picture stuff, where they keep a separate set of counters for the target picture and the source picture. We haven't done a lot of that in class. I tend to avoid that if I can, but there are times when it's just the right way to do it. So 4 minutes left. Ask a cool question. Anybody? Here or at home? We don't have time to do a more complicated version of lowering the frequency without making it quite as muddy. But I think you could work that out probably from some of the previous examples. Hopefully, don't know. Yeah, there we go. If we explore slow plane and we explore airplane, we can see that they look very similar. You know, you get the same basic structure, sort of a big blob, some quiet stuff, and then another blob that tails off. Oh, this is too high. But if we zoom in, I think, well, it's not super visible here. There, like, one way to see it is right here. This peak has got a flat top, and that flat top is because that sample got copied twice. And there's probably like flatness. Like I think there's a little flat space here. So there's some flat spaces. This looks like this has got a flat top here. The way it's drawing it, it's not as clear as I thought it might be that, you know, we're doubling all the frequencies. But if you look carefully, these sort of flat spots, I think, are suggesting the fact that we're doubling the frequencies here. If we, let's see, zoom back out, we click out here and we click out here, we can see that this is sample, oh, hello. Does it not tell us? Oh, yeah. Oh, it tells us the indices at the top. So this is sample like 13,000 up there, and this is like 28,000. So you can see that this is a lot longer when we doubled it. So. Okay, any questions about any of this before we wrap up? Otherwise, I will see you fine people not on Friday, although I will try to be paying attention to Slack as circumstances allow. And I will see everybody on Monday. So, okay, see you later. Ciao.